Wayne, Alex, hey you guys. Just want to tell you, Tech Talk Tuesday is starting up right now. Getting a few little more things lined up. Got some more interesting things to talk to you about tonight. Hey Travis, Rodrigo, and Alan, Tom, hey y'all. Thank y'all for joining. So, cylinder seal, ring seal has been very, very important that we've been talking about for years and years, and I drew a little Tech Talk number 55. Y'all believe that? 55 weeks in a row? Imagine that. All right, I'm gonna start over here. We have then in our mind a cylinder sleeve. You know, it's just where the piston goes up and down in the bore, and I drew a cutaway of the cylinder wall, and we imagine the OD of the sleeve to be smooth and the ID of the sleeve to be smooth. And then we buy this sleeve, and in reality, if you blew it up really big in a microscope, this thing would be super rough. It would have a really jagged finish that would like drag your finger. You could file your fingernails on it based on how rough it was. And then we put it in the boring bar, and we bore it out with a sharp bit, like a tool bit, is sharp. And we bore it out. Maybe we're smart enough to put a little back cut so we have less sharpness here. But anyway, when you bore this out, you have to tear. You have to tear the material away as the boring bar goes down the sleeve, and it's ripping through, cutting this steel or this cast iron or this ductile iron, and it leaves a really rough finish right here. It's rougher than the bore finish. I mean, than the, a really fine, smooth finish, and then you bore it. Now you've got really, really rough. Now we're going to blow it up even bigger here. We're going to blow up this, we're going to magnify, not blow up. I've been blowing up stuff my whole life. I'm going to magnify this cylinder wall even more. And this is with 100, 200 grits hone stone. It's where you take the stone and you go in here and you hone the cylinder out to get it to size. And I want you to see, if you have a really rough grit stone, this might only be 1/4 of an inch or maybe 1/8 of an inch of the bore, magnified really large so we can see the imperfections. Now, this is a very important step for cylinder boring and honing. It gets misunderstood, and I'm going to give you my normal disclaimer now, because I'm not a know-it-all. I don't know everything. My day job has been all of this for the last 40, 50 years. So I'm 66 now. So I started messing around with hot rods when I was 16 years old. Started racing go-karts and quarter midgets when I was a baby. But anyway, it stuck to me, and I've been learning a lot. So I don't do everything right, but I learned a lot of things not to do. And one thing that I have learned is this is very important. This deep groove. This is very, very important. So you're saying, well, wow, my cylinders look smoother than that. They have a cross hatch. They have a beautiful cross hatch finish. Like if you look at the bore, I mean, it's like, you can see where the hone stones was in here like this. And all of us have seen the cross hatch on the cylinder walls. Well, this is from the rough hone to rough it to size. I'd say you'd get within 4 or 5 thousandths of the finished size of the bore. And then we're going to move to the next smoother stone. And we're going to, when we hone it to the next smoother stone, we don't make the grooves any worse. But what you see now are the peaks. The peaks are now rounded off. So it's less abrasive, but you still have the deep grooves. Now we're getting close. Maybe we're within 1/1000th of the final clearance we want. Let's say our piston needs 5 thou clearance here. So you'd measure this piston, and then you would measure the bore, and you would want it to be 4 or 5 thousandths bigger than the piston. So I'm gonna show you what the next finish is, okay? Please understand, this is my opinion. This is not written on the internet by some ring or piston manufacturer. This is just the way we do it here, and it works for us, okay? So when we finish going to the next smoother grit, you can see that now these peaks, I'm just goofing them up, these peaks are now nice shallow peaks, all right? That nice low peaks. So, but these grooves, these deep grooves are still here. So if we kept honing till it got to be like this, if we honed it until it was glass smooth, like if it had a glass finish, it would burn these pistons up because a smooth finish cannot hold oil. That's why this is very important, these grooves. Okay, not the sharp grooves, not the sharp peaks, but the valleys. Okay, can you see? Yeah, you can see here. This valley fills with oil. And it creates, when this fills with oil, and then you polish off the peaks. If you polish off the peaks, now your cylinder wall is really smooth. But if you'll look, you still have these grooves that are pockets of oil. And they're in a crosshatch. They're in a crosshatch as the stone rotates and goes up and down. The hone goes up and down in the bore while it rotates, okay? Now, these pockets of oil are very important. These hold the oil that lubricate the pistons. They are what lubricates the piston. Now, the piston has to have the right clearance and the right finish here in order not to burn this up. So our piston that we use here for our T124 is this piston is coated with a really nice moly coating, and it's very smooth. There's 100 different shapes. I know looks pretty elementary, but this has got barrel and cam grind to it. It is a very unusual shape. Back in the day, we used to do them with lathes and stones, and now it's so complex, it takes a really high-quality CNC machine to put the finish on these that we use. These are real high-quality pistons made for us. Now, when this clearance gets right, we want to make sure we keep these grooves. So there's some real technical numbers. It's called RVK, RPK, and RA. The RA is the overall finish. I think like a mirror might be like 0 or 1, and then you can have a real rough finish, and you can have an RA of 10 or 20. And then the RPK would be what these peaks, the height of these peaks, and the RVK would be the depth of these valleys. And there is a number, there is a group, there is a combination. It's like having the right heads, the right cam, and the right throttle body, and the right exhaust. You got to have a combo, because one of those things without the rest is no good. So if you had the right RA, and you had the wrong valleys, and you had the wrong peaks, you would still have a really bad sealing cylinder. So I just wanted to share that part with you guys so you could understand. Now we're going to move on once we get the finish right. It's a crosshatch finish, and it's made to be smooth and straight, and Total Seal makes the rings for us, and they're really, really high quality. These rings are made, you're not going to be able to see it in this video, but you have to understand it's a diamond ground to flatness. They are so even in the width, radial width, axial width, and the finish on them. They have a real diamond-like coating on the face. This is our top ring. This is a 4 1/4 bore. I mean 4 1/8 bore. And this ring is not really too aggressive. It has low tension, small in width. It's very lightweight. And the competition, what most of the people are using, that when their engines get here or our competition uses, they use this ring, which is a standard 062, 064 ring. It's really wide. It's really thick. And this son of a gun right here has some tension, like you can hardly squeeze it together. It's got a lot of tension. Now this tension, this makes it, it wants to stay open. And when you compress it on the piston and you put it down in the cylinder, it wants to spring back open. And that pressure springing open is what keeps the ring sealed to the bore. I'm going to blow up. This is an exaggerated picture of the ring touching the bore. You can see why it's so important that you have a really wet and lubricated surface here and a really well-finished surface here. And these two parts have to match each other. It's a lot like how back in the day we used to have to put lightweight springs on the solid lifters in order to run them to break a cam in so that we didn't push through the oil. There's a lot better oil nowadays, but if we could visualize this layer of oil here, this layer of oil that has feet, or like it grabs into these grooves, and it makes a barrier, a safety barrier, to lubricate the rings from the cylinder wall, to lubricate the rings from burnishing or burning the cylinder walls. Okay, I want you to also notice this ring, how wide it is. Imagine if we were to, I gotta draw a better picture. That's pretty weak. I'm gonna exaggerate the barrel finish. That's not really exaggerated, that's about right. The only place that contacts this ring is in the center. Okay, if this was the cylinder wall and this was the ring, this is exaggerated. How much of this ring is touching the cylinder wall? That's right, same amount as a tire touching the ground. It's just the contact patch. Goodyear made that famous contact patch. This ring's heavy, it's thick, it has a lot of tension. So what we do is we cut this ring away here and here, and we have Total Seal make these rings for us that are thinner and lighter, and they have less tension. I'll give you a visual here. Here's the regular old conventional 16th, 062, 064 ring. It's really thick radially versus our Total Seal ring. You can see how there's probably less material here. This ring is 036 wide, actually, and this ring is 062 or 3 wide, width versus width. Can you see the difference? This one weighs half of this one, and I'll tell you about why that's important in a few minutes. But please notice that the same contact pattern is here. We have not changed how much of this ring is touching the cylinder wall. So if you were going to build a pro stock motorcycle or a pro stock car engine and you were going to rev it to the moon and you wanted ultimate ring seal, what would happen if you cut this much of the ring away and you went to a ring this thin? Now we're talking a 25 thou, 24 thou width ring versus a 64. Let's say this one is 024 wide here to here, and the one we had on it before was 064. Same contact patch, same pattern on the wall, but this material is gone. Now, this is mass. It does several things. It adds a lot of tension to the cylinder wall. It wears out the walls fast, and it wears out the rings really fast because it's so stiff and strong. Still a barrel face, still has a ball finish on the front so it touches in the center. Versus the little thin ring we use on our pistons, 036, nice barrel finish, and it has low tension. So this actually wears the cylinders out less, wears out the ring less. And another thing that gets left out by a lot of builders is this piston right here. And the combustion chamber, as you know, has got the valves in it. Well, that's the roof of the combustion chamber. This is the floor of the combustion chamber. This is the floor. So I'm going to draw a little sketch so you can see. The piston is here, and here's the dome, and the combustion chamber is here. So this is the ceiling of the combustion chamber where the spark plug goes in and the valves are, and this is the floor of the combustion chamber. Whatever the heat is in there, if the heat in the combustion chamber is 800, 900, 600, 1,000 degrees, whatever the temperature is, the piston crown, not a great name, the piston crown gets the same temperature as this. So guess how we cool this? How does this piston cool? Well, some of the new engines have oil squirters that squirt oil right beside the crankshaft. They squirt oil in here to cool this crown off. A lot of people think those are wrist pin oilers, or they think they're crankshaft oilers, but they're not. They're piston cooling jets. Piston cooling jets. That's what those squirters are that squirt oil up in here that come out the side of the cases under the piston. All right. Also, this piston, let's say, just to call a number out, let's say it's 800 degrees on the crown. Guess where that temperature goes? It goes right into this top ring, and this top ring has to dissipate that heat out of the piston crown through this ring into the cylinder wall. And on our motorcycles, the cylinder wall is an iron cylinder pressed in the sleeve, and the outside has fins on it. You know, big air cooling fins, right? So this ring transmits the heat out of the piston into the cylinder wall, out of the cylinder wall into the cylinder, the sleeves, and the temperature and the air blowing on it gets rid of those. Now, in a car engine, there'll be a thinner jacket here, be a thinner sleeve, and this will all be water. So you have a radiator in your car, and this is all full of coolant. And this piston takes that 800 degrees that's in this piston crown, puts it into this ring, and this ring transfers it right into here. And then you hope this recirculating coolant pulls the heat out of this bore so that we can maintain the sizes, the dimensions, the clearances, so that we don't burn up parts. And we make a lot of horsepower. Very confusing. I heard on a NASCAR racer talking about information overload. It's like drinking out of a fire hose. When you get too much information at once, you don't know what to do with all of it. I got a couple more things I'm going to show you about that, and then we'll move on. All right. Everybody follow me so far? Scene, Rob, Jimmy, Daniel, I see you guys. Thank you all for watching. Thank you so much for tuning in. It's a real blessing for you guys to come look. Thanks. Here's a cutaway, a side cutaway of a piston. I just took this drawing and put this as the top land, the second land, the third land. I got a top ring, a second ring, and an oil ring. Here it is. Top ring, second ring, and an oil ring. And I'll try and draw those in for you. That's a cutaway of the top ring. Now you can imagine, here is a competition, one of our competitors. This is, you can see how big and thick this top ring is, right? It's just a real thick one. This big ring fits in here. Pretty tight clearances. Who knows what that clearance is when it gets hot. When this gets up to 600 or 800 degrees, who knows how far this opens up, but it does. Now, the cool thing, and this one got so hot that the second ring stuck to it. This second ring won't even move. And I'll tell you about that too. But when this has combustion chamber pressure, here's your head gasket, and here's your cylinder head chamber. All right, when you get, didn't do that right. I caught myself wrong about that one. All right, here's the cylinder wall. Here's the head gasket. And then the head bolts on here, and the combustion chamber looks like this, or you hope it's like this. Now, all this fire and all this pressure in here comes down the side, and the only way this ring works is for this pressure to leak down beside the piston, get in on top of it, get behind it, and push it out. That's how this piston works. This piston has the combustion chamber pressure, 800,000 psi, plus temperature is close, has the pressure's on top, big pressure, 800, 1,000 psi, goes down the side, runs down the side, goes in on top of the ring, gets behind the ring, and shoves it out on the power stroke. Now, we use gas-ported rings. We gas-port our pistons, and we use gas ports to take this friendly friendly, thin, lightweight, unobtrusive. It doesn't wear out the cylinder walls as much because it is tool steel. It is a real high quality, high temperature ring. But it has to be because now we're taking away the capacity for this ring to dissipate the heat out of the crown into the cylinder wall. And the smaller the ring is, the less heat you have, the less capability you have to transfer the heat out of the piston into the cylinder wall. So you have to have a real high quality ring that can handle the heat. Now, some of these are cast. Some of the top rings our competition uses are cast. They're centrifugally cast. They're ductile iron. They're made for handling heat, and they have a lot of pressure. This one's tool steel, and since it doesn't have much radial pressure here, we use these gas ports. Instead of having to get down here and get behind this top ring and go behind it and push the rings out, we use the gas ports to actually fit. Now we can have a better clearance here. It's really tight, very little leaks, not much combustion pressure comes down the side and goes behind the ring and gets behind it, not much. Most of it comes through these holes. Now, the old tale, the old story, the old rumor is don't use gas ports because they wear out your cylinders, they wear out your rings, they don't last as long. Well, I beg to differ because this ring wears out your cylinder wall. This ring wears out the rings because this ring is an enemy to itself. It's too big, it's too heavy, it's hard to control, and in order for it to work, you guys, in order for this ring to work, this big heavy ring, is you have to put it in here loose. You have to put it in here loose enough for the pressure to get behind the ring and blow it out. I'll try and draw it again. Blow up the ring, expand the top land. Okay. The big heavy ring sits on the bottom of the land when it's sealed up. It has a beveled corner here. You can take this ring right here, this big heavy ring, and you can see the bevel. Let's try and find it. Sharp edge on the bottom inside, bevel finish on the top side, okay? This is the bevel, and this is so that when this pressure builds, when the spark plug lights and it blows up, expands, and the chamber and the combustion pressure has to leak down here, it has to run in here, and it has to go out and push this ring out to the cylinder wall. Now, we have seen what they call radial gas ports, and they're drilled here. You guys may have seen them. They're drilled on the side of the piston right here. They drilled all the way into the back of the ringland, and what that does is the same thing. The combustion has to travel the same distance, and it goes through this groove, through this hole, and then it gets behind the piston. And when this pressure builds up, not behind the piston, behind the ring, when the pressure builds up behind the ring, it pushes this ring out against the cylinder wall for ring seal. Now, I like the gas ported ones better because there's nothing going on. You can have a full deal here, and then you got a hole drilled right through the top of the piston. So when the pressure gets big in here, it goes right down this hole and it gets right behind this ring and blows this ring out. That's what a gas port is. I don't know if I'm being too goofy for you to understand. And I see people asking good questions. There are good questions, like the new gas ported rings. I'm not going to talk bad about anybody's product. I'm not going to brag on anybody's product. Yes, I am. Total Seal makes them. Total Seal is my ring of choice. Total Seal gives me the choice to decide if I want what I want from them. They make great products, and I've used them for a long time, and I'm very thankful I have, because they have elevated our program. They have helped us, and they've trained us a lot. When we were confused and we didn't know what we were doing, they helped direct us into where we were going so we could do better. This is a cutaway drawing of the big heavy ring. It's big radially, big axially. I don't know how to say it or spell it, but that's this way. This is radial. Radial width on this ring is big, and the axial width is big. Our ring that we sell and supply with our Star Racing Power piston kits for your M8 and your Harley Twin Cam uses this thinner ring. high quality. Oh, a set of these rings cost half as much as a set of these rings. So when you buy our kit and it costs a little more, part of the reason is because these rings cost twice as much as these rings. You can buy a set of these rings cheap, $10, $20, whatever. Maybe there's some $30 kits out there, real nice 3-piece rings. But this one here, these cost a lot. These rings are like $25 a piece, not for a set. They cost a lot of money. These pistons are made for us to fit those rings, okay? Now, Dykes rings aren't really used on much anymore. It was a good idea as well, but several things have happened over the years. The RPM level has gone up. A lot of engines were turning, 6,000 was a high RPM engine, Harley, V8. Now there's engines out there turning 12,000. We have Suzuki Pro Stock engines turning 14,000. And these rings are really, really important at high RPM because this is going to be my last piece, and I'm running out of time, but I want to share this with you. This ring right here it got inertia. When the piston goes up on the exhaust stroke and the piston stops at TDC, this ring keeps going. And when the piston turns around and the crank rolls over and the piston starts coming back down on the intake stroke, this ring is following along behind. And then you got to compress the mixture, and then the spark plug lights, and then it's going to go bang, and this has got to keep all the pressure above it. That takes 720 degrees of rotation, so the rings are only getting used, they get used for intake, create a good seal when the piston goes down to pull atmosphere in from outside to get into the cylinder, and they also have to do a good job when you light off the spark plug and contain the pressure above this ring. You want this ring compressor to stay from this ring up so that it pushes all the pressure and all the power on top of the piston to rotate the crank. When this ring, this heavy ring, that weighs twice as much as our ring, when this ring goes up 200 times a second to make power, when it goes to the top, the piston stops, the ring keeps going. And when it does, it loses seal. So 200 times a second, this ring loses seal with the piston. And the seal is this land right here. This is where the ring seals, right here. So the ring, shaped like this, and the piston has a perfect finish here, and it has room up here. So when this has got combustion pressure blowing through the crank combustion chamber, it goes back here behind the ring and pushes. This better be sealed up. The way we do it to get better ring seal and longer, and they last longer, is we make this tighter and we drill the hole through here to get the pressure behind this ring. Okay, I've said that enough times. Like somebody told me one day, you got to land the plane, man. You got to quit circling. This last thing, oh yeah, I still got a couple people watching. This top land, can you see this okay? Top ring goes here. This is an accumulator groove right in between the top ring and the second ring, and then this is the oil ring. This design piston, because this engine has a lot of stroke, they have put this really big ring in here, they put this really big ring here, and they got this really big ring here, and they got the wrist pin shoved up in the oil ring. I'm not a fan of that. So another good advantage of using the little rings is we can run them up a little closer, we can run the second one up a little higher, we can run an oil ring up a little higher, and we end up with enough room to get the wrist pin under the oil ring instead of behind the oil ring. There's a lot more technical talk to this, you guys. Thank you so much. I'm sorry that it took so long for me to land that airplane on ring seal and how the pistons work, but I just wanted to share it with you guys. And also, I'm very thankful that I've had you guys come in and see us and talk to us. Send me messages, send me email, george@starracing.com. You can IM me, Instagram, Facebook. I respond to people wanting to know more and talking more, and I'm sharing it because I've been studying it for a long time, and I love sharing it with you guys. Anyway, stay tuned. Thanks for watching. May God bless y'all.